All right, so combinations. Everything that we've looked at in terms of the specific examples from 11.1, although we talked about what a combination is, all of those examples were permutations. They were situations in which order mattered. A combination is not so much an arrangement, but a grouping of objects where the grouping doesn't matter, right? Or the order of the grouping doesn't matter. So it's, whoops. A grouping of objects in which order does not matter. Okay? When all of the objects kind of go into the same container, if you think of it of a sort of figurative container, then you can kind of think that that could be a combination. So I gave the example of fruit salad because all the fruits are going in the same bowl, and it's easy to think of the container in that case. But even putting people into like a group for a school project, right? You're all going to the same table or whatever. Yes? Yes. Combinations tend to be easier than permutations. Yes. Not always, but often they are easier. Yeah. Okay. Now, for example, so some examples of where you see this is anything where objects go into the same container. Right? So for example, salad, soup, smoothies, something like that. Or you could even think of it as items in a bag. Like let's say you go trick-or-treating and you get all these different candies. The candies are all going into the same bag. Right? That's also sort of like a grouping. A team without positions. Right? So if there's a sports team and the sports team doesn't have, players aren't given specific positions, that would be a combination. It doesn't matter sort of what order the players are selected to be on the team, they still are on the team, right? Once you start saying, well, you were selected to play goalie and you were selected to play left defense, and right, that's a bit different because now they are going to specific spots. Similarly, something like a committee or a school group or something like that, where there are no positions. Okay. If we look at, for example, the letters A, B, C. Okay. And Scrabble is a really great way of thinking about the difference. There are 6 different arrangements of those letters. Okay. So there are 6 permutations. There are 6 ways that you could attempt to arrange them on a Scrabble board. Of course, a couple of them will get thrown out because in Scrabble they have to also be words. But you could try. There would be 6 possible arrangements, but there's only one grouping. If those are the letters that you have on your little Scrabble tray, it's still the same group of letters, right? So only one grouping or combination. There's only one way to combine those 3 letters. You combine them as ABC. Makes the group. Doesn't matter what order you pick the letters out of the Scrabble bag, you still have the same letters to work with. Okay? Now, there is, as you can imagine, there's going to be less combinations than permutations, okay, when you're dealing with a specific number of objects. The formula, NCR, so if you have n objects and you're only combining R of them, let's say I want to make a group of 5 out of this class, and there's 26 of you in the class, so it'd be 26C5, or combined 5, is n factorial over r factorial times n minus r factorial. So you can see actually the n factorial over the n minus r factorial piece is the exact same as the permutation formula. But what we do is divide by r factorial, the number of ways that you would be able to arrange those r objects, right? So that's sort of the difference, and that's where it comes from. We have to divide out those arrangements of the r objects, okay? The other way that you will see this written is like this. That means the same thing. Okay, and I think on your formula sheet you have both. Let me see. Yep, you do. You have both of them just right down here. Okay, the button on your calculator for the NCR is in the exact same place on both calculators that you would find the factorial button and the NPR button. Okay?
Wait, so is it like a fraction, like you put a line there?
Okay, so let me show you an example. Let's say, for example, how many ways can you make a group of 5 students from a class of 26. Okay? Order doesn't matter. They're not standing in a line. They're just making a group. You're putting them together at the same table. Okay? So if it was a permutation, it would be n factorial over n minus r factorial, right? But that's where order matters. So we got to divide out 5 factorial. The 5 factorial represents the number of ways that you would have been able to arrange those 5 people, right? So you would write this as 26C5. And people will also either use the word choose or combine. You'll say 26 choose 5 or 26 combine 5, okay? And that is equal to 26 factorial over 5 factorial times 26 minus 5 factorial.
So if we were given a second formula, you would still write it in that format? Oh.
Over 5 factorial times 21 factorial. These two numbers always add up to that one, right? Now you could do this on your calculator, or like the combinations are actually not too hard to do sort of on paper, because remember, a ton of these are going to cancel. Everything from 21 down will cancel, right? And then you have to figure out how much is 5 factorial, divide that by the numerator, whatever's left in the numerator. But there's also just a button on your calculator on the TIs. You have to put in the 26 first. And then you go to the math button. Just wait for it to load. Okay, so you put in the 26 first, the n value, and then go to the math button, it's down here, and go over to the right to probability, and then it's number 3. 26, choose 5. So there's 65,780 ways that I could make a group of 5 students out of this group of 26. That's a lot of different groups. It's a lot. What was it? 67,000? I can't remember. 65,780. Okay? All right. So, for example, how many ways can the debate club coach select a team from 6 grade 11 students and 7 grade 12 students if the team has 4 members? Okay, so if there's 4, if you want to make a team of 4, well, how many students do you have to work with? 13, yeah. 6 in grade 11, 7 in grade 12, so 13 students total. And we're choosing 4 of them. 13, choose 4. Now, honestly, I personally, it's going to be 13 factorial over 4 factorial times 9 factorial. For this kind of thing, I find it easier to kind of do on paper than have to take out my calculator and punch it out, because I know that everything from 9 down is going to cancel here. So what I would do is go 13 times 12 times 11 times 10. Now, 9 down will cancel with that. And then I just go over 4 times 3 times 2 times 1. And then I'm like, oh, 4 times 3 is 12, so I can cancel that and that. 2 over 10, that would make 5. And then on my calculator, I'm like, okay, 13 times 11 times 5, whatever that is. I don't know what it is. 55 times 13. $750. Right? But you can also just use that button on your calculator. Okay. Okay, so what about this? 4 members, only one of whom is in grade 11. Okay, so you got 4 members, 1 grade 11, then how many grade 12? 3 grade 12. So what we actually have to do here is figure out, we need 3 grade 12s and 1 grade 11. Okay, so we have to think, if we have 7 grade 12s to work with, how many ways can we make a group of 3? Yeah, so this is 7 choose 3. Then we have to multiply that by how many ways can we choose 1 grade 11 from a group of 6. 6 choose 1, yeah. 6 choose 1 is always 6. Yeah, anything choose 1 is n choose 1 is n, right? Because if you have n objects, you're only choosing 1 of them. There's n ways to do that. And that is, I don't know, whatever it is. It's 35, I believe. Is this 35? Times 6. That's 210. So as soon as you put, this is kind of how restrictions work with combinations. As soon as you put this restriction in there, it greatly reduces the number of groups that you can make. Okay? All right. So far, so good? Okay. All right, combinations with cases. These work exactly the same as permutations with cases, in that you need to look out for those 3 or those 3 phrases, or at least at most. Okay? And you have to figure out the number of combinations for each case, then add them all together. Right? So this is very similar to cases for perms. Why can I not write today? Right? We need to identify cases, determine the number of combinations for each case, and then add cases together. Okay. So for example, You are writing a social studies exam, and they say you need to answer a specific number of questions from each section. How many different selections are possible? If you must answer 2 of 4 questions in part A and 3 of 5 questions in part B. Okay? Is this question a case scenario? No. Because you have to do 2 out of 4 and 3 out of 5. Okay? So this one is actually really similar to the debate question that we just did. You have to choose 2 out of 4 questions from part A. So that would be 4 choose 2. This is part A. And then times 5 choose 3 for part B. Okay, and that is, I think this is 6. And this is 10. Shoot, I'm doing these in my head. I hope I'm right. Am I? The way that I do it quickly, by the way, is like for 5 choose 3, I'm like, okay, well the 3 times 2 times 1 is going to cancel, so it's going to be 5 times 4 over 2 times 1. That's how I do it. So that's like 20 over 2 is 10. That would be 4 times 3 over 2. Yeah, I think I'm right. But again, you can use the calculator if you want. Okay? B, you must answer 2 of the 4 questions in part A and at least 4 of the 5 questions in part B. Okay, is this a case scenario? Yes. Because you could answer 4 questions in part B, or you could answer all 5 questions in part B, right? And sometimes, I don't know if they do this here, if your social studies teachers ever do this here, but it's not uncommon. Like, I'm trying to remember if they did it in high school in various courses where there'd be sections you had to choose 2 out of 3, but some teachers would say, shh, if you answer all 3 questions, we'll mark all 3 of them and take the best 2, right? So that might be a scenario where you could do 4 or 5 kind of thing, okay? So case 1, you do 2 from A, and let's say 4 from B. And case 2, you do 2 from A and all 5 from B. Right? So 2 from A would be 4 choose 2 times 4 from B, 5 choose 4. This would be case 2, 2 from A is still 4 choose 2 times 5 choose 5. Okay? 5 choose 5. If you have 5 objects and you're choosing all 5 of them, how many ways can you do that? 1. Yeah. So this is 1. This is 6 times 5 plus 6 times 1. So that's a total of 36. 36 different ways you can do it. I feel like they used to do that in university sometimes. They'd give you different sections and you could choose which questions you wanted to do from each section. What's that?
I wish they did that.
Yeah? You know, maybe I'll bring that back in Math 31. I like that idea. Maybe I'll do that. Okay. A bag. We're going to stop here for today. A bag contains 7 black marbles and 6 red marbles. How many ways can you draw groups of 5 marbles if at least 3 must be red? Okay, at least 3 must be red. Yeah, 3 cases. So what are the 3 cases? So we're drawing 5 marbles. We need at least 3 of them to be red. So let's suppose 3 are red. Then how many black would you have?
2.
Right, so 2 black, 3 red. Case 2. We need at least 3 to be red. What's that? You could have 4 red. Yeah, that's right. So you could have 1 black and 4 red. And then case 3 is 5 red. Yeah. Okay. So this first one, 2 black. How many? We've got 7 black. So this would be 7 choose 2 times 6 choose 3 plus 7 choose 1 times 6 choose 4 plus, if you wanted to do 7 choose 0, you could. If you have 7 objects and you're choosing 0 of them, there's only one way to do that. So it's just going to be times 1 anyway. So you can just put in the 6 choose 5. Okay? But that is 7 times, this is 21. Times 6 times 5 times 4 over 6 is 20. Think. This is 7 times 15. And this is 6. Man, I really hope I'm not getting over ambitious with doing these in my head. So what is that? This is 420 plus 105 plus 6. So that's 431 altogether. Different ways that you could do it. Yes. No, 531. There we go. 531. Okay, so I think I'll end there for today, and we will pick up with the rest of combinations tomorrow.